Today's talk is going to focus on the metrics in compound design. So what is hoped that we're going to be learning throughout this talk is we're going to focus in on is there any additional guidance towards compound design. We may have already learned about the physiochemical properties with Lipinski, but is there anything that guides us all the way from hit validation and hit optimization all the way through to preclinical candidacy? What are these guidelines? Well, in this talk, they are going to be referred to as metrics. We're going to see about how we make meaningful changes to a molecule in order to make a final optimized compound. So before we begin understanding the role of metrics, we first must be able to understand the role of physiochemical properties. Please also refer to some other talks outlined by the WCare online series. However, what first we must learn is that as a compound starts to move through the drug discovery process, it gets larger in molecular size, as well as it also increases in its lipophilicity. As you can see by this diagram represented here, is that we see an almost linear relationship between molecular weight and lipophilicity. However, by increasing just, for instance, lipophilicity, we can sometimes lead ourselves into non-specific binding and potentially other issues such as cytochrome P450 inhibition, hERG inhibition, as well as many others. So what guidelines do we already have in place? Well, we've already learned about the Lipinski Rule of 5. Lipinski undertook a study of almost over 2,000 oral bioavailable drugs, and he came up with a set of parameters that enables you to be able to make an oral permeable drug. However, is just Lipinski's rules enough? And so far you should be questioning and by saying, no, it's simply not enough. In order to start understanding about metrics, we first must be able to understand what sort of chemical matter are we working with. We have two different types of screening outlined here, known as high throughput screening, HTS, or fragment-based drug discovery given by FBDD. And how do these two chemical matters differ from one another? Well, with a high throughput screening molecule, you can see here it's already of a substantial size. It doesn't interact with its binding site particularly well, but it occupies a large proportion of it. These bindings are often lipophilic in nature because polarity or hydrogen bonding is very directional, and your high throughput screening molecule may not have the correct geometries to allow for optimal binding. However, the opposite can be said for a fragment-based hit. Instead of using lipophilic interactions, these are often made through polar contacts. But being a fragment part of a molecule means it's relatively small and only occupies small portions of the active site. This occupancy is reflected with its very poor potency values in comparison with high throughput screening hits. Now we want to be able to understand how to improve potency and what does this relate to when we're looking at our molecule. To improve the potency, it is said that you need to see an increase in the negative free energy of binding, which is given by delta G. Delta G, however, is comprised of two values, mainly enthalpy as well as entropy of binding. It's said that being able to assess this value of your molecule, that you are able to gain an understanding of how a ligand progresses through the drug discovery process. Looking at enthalpy more, to optimize polar contacts, you see an increase in enthalpy, and therefore you see an increase in the delta G value. However, the opposite is true when you start optimizing for non-specific interactions. Non-specific interactions sees a favor more towards entropy rather than enthalpy, and therefore your delta G value has a tendency to decrease. So what does this mean when it all comes to metrics? We have an understanding of the delta G value. We know that we need to build our molecule in a logical way, but how do these two values relate to one another? They can be composed into a calculation called the ligand efficiency calculation, which is comprised of this delta G value, but also as well of atoms, the number of atoms that are present in your molecule that are non-hydrogen species. HA is represented as non-hydrogen atom, and it can often sometimes be written in literature as HAC, which means heavy atom count. By treating the data in this way, you make two assumptions. It assigns all of the intermolecular interactions to the ligand alone and it assumes that the binding energies per atom are additive. What also must be noted as well is that delta G can be represented in many different formulas. Here you have the formula as seen on the opposite page, using enthalpy and entropy to gain its value. However, often we don't actually measure this. What we do measure is we measure potency, here given by the dissociation constant, but often we can substitute this for our PIC50 values using this equation here. What ligand efficiency does is it treats or weights your molecule as a whole and scores it against its potency value. How does it weight it? It uses the heavy atoms in the molecule. These are, for instance, heteroatoms, carbon, halogens, but it treats them all as equal, rather than different, as in they're different sizes, they're different electronics, they're different functionalities when they are within your molecule. You can see that this potentially is a disadvantage, and this will be discussed later on. So if ligand efficiency treats your molecule as a whole and relates it towards binding, there must be a penalty and there must be a reward. What's the penalty? If you have a molecule of already a substantial size and you don't see any or minimal increase in potency, you know that whatever you've added to that molecule is not contributing towards binding. And ligand efficiency shows this by showing a decrease. Again, the opposite is true if you were to minimize the amount of atoms added, but you see a bigger boost in potency. Therefore, you see the ligand efficiency value increase. And this saying by Reynolds says that your heavy atom count is actually the currency, and you want to have the best value for your money. So spend less to achieve more. So what is a good ligand efficiency number? Well, it has been postulated of 0.3 kilocalories per mole, and it should be noted that ligand efficiency has its units of kilocalories per mole. So why was it 0.3? With an average molecular weight of 500 and a non-heavy atom count of 38, requires a ligand efficiency value of 0.29. This is if it's going to have a binding affinity of 10 nanomolar. This is almost a drug-like candidate. So this guides us that a compound should, in theory, have acceptable or reasonable physiochemical properties to make it all the way to a drug-like candidate. What therefore you should be noting is that ligand efficiency can actually increase or decrease as it moves through the pipeline. Here, for instance, you see a HSP90, the heat shock protein 90, fragment-based drug discovery program. What they did was they took this fragment-based hit and they started to optimize and drive their potency in the correct direction. You see that molecular mass is being added to the compound. Also, you see a boost in potency. This is therefore reflected in its ligand efficiency value. You notice that it starts to increase, and increases sometimes dramatically. All these values are above 0.3, meaning that your molecule is contributing well as a whole to binding in relation to its potency. However, when you actually look at these two molecules here, this one and this one, you will notice that there's actually only an addition of 6 heavy atoms, but look at the boost in potency. It has increased by over 1 million fold, and this is showed in its ligand efficiency value. This compound is binding very well to its target and using all of its atoms to do so. However, you can see here for the last molecule outlined here that its ligand efficiency value starts to take a decrease. Have we done something bad? So let's look at the potency value here. The two potency values here, there's not that much of a difference, but you can see the difference by the addition of this piperazine moiety at the end, that we are adding on a substantial amount of mass. The mass also, we are adding in some polar species, but we are not seeing such a massive boost in potency. Yet our ligand efficiency value is telling us we are still ligand efficient, we are still hopefully going to have those correct physiochemical properties later on, but we've just made a slight decrease. How is this influential? It should be noted that even though there was a decrease in this process, this compound actually went on to go through clinical development for the treatment in cancer. We discussed earlier that heavy atom count doesn't distinguish the differences between, for instance, carbon and some of the heteroatoms. It can't distinguish between polar and non-polar contacts, but we know that to have polar contacts in our molecule, we are increasing the enthalpy, hopefully, and we are also increasing the delta G value, thus boosting an increase in the ligand efficiency. By weighting all these molecules the same, you cannot say whether you're making these specific interactions, these hydrogen bonding, these polar contacts, or if you're making these non-specific hydrophobic lipophilic interactions. You can just see here by taking these two molecules that we are increasing or adding on polarity into the species, yet the ligand efficiency value is staying the same. Okay, we see a boost in favourable direction of both potency and lipophilicity, but our ligand efficiency value is staying the same. It's not really giving an indication as to what are we changing in our molecule. We need to ensure that we add on species, add on functional groups in the correct and right places, and that we're doing it for the right reasons and not just to gain a boost in potency through non-specific interactions. There is this phenomenon known as the magic methyls or the methyl phenomenon, whereby the addition of just a simple methyl group, the potency can often be boosted by putting this methyl group into the correct place in the molecule. But again, do you know this is meaningful? You shouldn't be adding grease to your molecule just to see a gain in potency that could potentially lead you to detrimental effects later on. So is there a way to distinguish this binding? And the answer is yes. We know that lipophilicity is a massive influence towards your absorption, distribution, metabolism, and excretion. We know that these non-specific binding interactions can potentially lead to off-targeting effects later on, for instance in the likes of cytochrome P450 inhibition, as well as the hERG inhibition related to cardiac arrhythmias. So by taking ligand efficiency into account, you can come up with another metric called the lipophilic ligand efficiency. And what it does is it bases the potency value in relation to your lipophilicity. If you have a very good potency value and minimal log P, you can say that the interactions your molecule is making is through polar contacts rather than through these non-specific lipophilic contacts. But how do we know what lipophilic ligand efficiency value is? It's said for a drug candidate that an LLE of 5 or more, with these log P values in the lead-like space of around about 3 and a potency value of 10 nanomolar, that it should have 5 or greater. However, as we are manipulating our chemical matter through the drug discovery process, we are not dealing with a drug candidate, we're dealing with a lead-like molecule. And as such, your LLE value will actually be lower than this, but you are seen to progress it as it moves through the pipeline. For lead-like compounds, a typical LLE value is roughly about 3. To put it into perspective, these different values of 0, 3, 5, what's good, what's bad. So here we've understood what something good looks like. With an LLE value of 5, you can say that your potency is being driven by these polar contacts because your lipophilicity isn't heavily weighting down this potency value. However, what happens if the opposite was true? What happens if you have something that's incredibly lipophilic, you still see potency? What happens to this LLE value? If LLE is 0, it says that your compound has a greater affinity for octanol than water, i.e. it is incredibly lipophilic, leading to these toxic effects later on. The potency is being driven through these non-specific interactions. Here is just an example to outline how important LLE is and how it is modulated through a drug discovery process. Here we have a potential lead-like compound for the bromodomain containing protein 4, otherwise known as BRD4. This lead-like compound, number 4, contains a CF3 group in this position indicated here. It already has reasonable potency, its log D is incredibly high. Now, from our knowledge already, we know that by having a higher log D, we limit our pharmacokinetic properties, such as solubility, such as stability. We start to negatively influence these values. The lipophilic ligand efficiency value, however, has indicated that you are doing something that is non-desirable. It's showing, remember, we wanted a value of 5. 3 to work with, but we're aiming to start to increase that value, and this number is actually low. So what they did is that they substituted the CF3 by just leaving it as the naked form as the hydrogen. And what they saw is they saw a dramatic drop in the log D value. They started to see some favourable properties, as in for solubility, but its lipophilic ligand efficiency value started to increase, and increase in the correct way. As you start to move through all these different modifications, there are large increases in the LLE. And this is through just simple modification at one site of the molecule. A small change can sometimes have a dramatic effect in the LLE. And you can see here for compound 9 is that by incorporating just this methoxy group, a polar handle as well, that your log D value decreased favourably. So how does ligand efficiency and the lipophilic ligand efficiency value interact, or how do they play a role with each other? You can see here by this diagram here that we've got ligand efficiency on the x-axis and we've got LLE on the y-axis. Indicated by the green lines that we can see the desirable ligand efficiency value, and we can see the lead-like desirable LLE value. This graph has been separated into quadrants, the first being the top. We can say that any compound that falls within this top region of the graph, that it is potentially using polar contact to drive its potency, while the opposite is said for the bottom, that lipophilic contacts are driving the potency. And how do we know this? The LLE value. The LLE value, if it is of a higher nature, it is saying it is driven through polar contacts. Of a lower nature, it is driven through its lipophilic contacts. But again, how does this relate to ligand efficiency? If you fall in this space of the graph here, you have a low ligand efficiency value and a low LLE value. Often molecules found in this region of the graph are potentially larger. Not all their molecules are contributing to binding, and they are perhaps more on the lipophilic side. Looking at a compound that has a higher ligand efficiency value but a low lipophilic ligand efficiency value, it is said that for the size of the molecule that it is using its atoms efficiently for binding, but perhaps it is also being done in a non-specific manner through lipophilic interactions. With a lower ligand efficiency value but a high lipophilic ligand efficiency value, you can say that your compound has some polarity associated with it, but perhaps not all the atoms are contributing to binding. The area of the graph that you want to fall in is the top right-hand side, where you have a high ligand efficiency value and a high lipophilic ligand efficiency value. From here you can say that most of the atoms in the molecule are contributing to binding, and with those contributions it is potentially being done through polar contacts. Ligand efficiency and LLE are not the only metrics that you can use. You have an abbreviated version of the LLE which was developed through Aztecs. Aztecs used this LLE-AT value with the use for the fragment-based drug discovery programs, and is sometimes often seen with other fragment-based drug discovery programs. And what this does is it takes into account the lipophilicity, just like the LLE. However, now it weights the compound based upon its heavy atom count and its contribution to potency. And you can see here by the formula on the right-hand side. Another metric is the group efficiency. So you've learned about ligand efficiency as the molecule as a whole, but how do we know through the addition of one functional group to another is actually beneficial? Well, you can use this group efficiency metrics. And here's just an example at the bottom. You can take a molecule that has a hydrogen atom, and you can replace this hydrogen atom with this aromatic group here. With the addition of this aromatic group, this hypothetical molecule sees an increase in 10-fold potency. You can see this by its ligand efficiency value, that it goes up only slightly. Why is that? Well, because there are a large number of atoms being added through the change from just the one hydrogen atom. And remember, with a heavy atom count, we don't include the hydrogen in its count. However, when we start to understand and look at how is this change meaningful, did it make an impact to ligand efficiency? The answer is no, it didn't. You can see that its group efficiency value is very, very low. And it says here actually, if you are to make this change, that you need at least a 22-fold gain in potency to make this change a meaningful change. There's an excellent paper by Hopkins that I would recommend that you read, and in it has a great set of tables where it has lots of different functional groups and the potency gain needed to be achieved by each of these functional groups in order to see something meaningful being added to your molecule, and you just aren't adding for the sake of adding. So I do recommend highly that this has been read. Another metric that's perhaps not used as widely but is still very important is the property forecast index. And what the property forecast index does, it takes into account your log D value in respect with the number of aromatic rings. We know that molecular weight increases as we move through the drug discovery pipeline, and often most of our drug molecules contain aromatic rings, 1, 2, 3, hopefully no more than that, but you can see that some drug molecules actually do contain a large number of aromatic rings. Aromatic rings bring with it lipophilicity. You can see here as we start to increase the lipophilicity value, as we start to increase the number of aromatic rings. Now it has a negative in many different pharmacokinetic properties. We discussed earlier that if you start to increase lipophilicity, you start to see some off-targeting effects. You also see some inhibition, as mentioned here by the cytochrome P450 enzymes. You start to see hERG inhibition, the human ether agogo-related gene inhibition, which is cause for cardiac arrhythmias. So what is an optimal PFI value? It's said between 5 and 7. However, a chemist can often look at a molecule and know that it perhaps has too many aromatic rings. So looking at this in a little bit further, how do aromatic rings actually affect some of these pharmacokinetic properties? Well, here is a comparison of just carboaromatics, as in aromatic rings that do not contain any heteroatoms. We have heteroaromatics, and we've also gone for the aliphatic chains, both with and without a heteroatom in place. And you can see that with the aromatic species, just a carboaromatic, that it negatively influences all these parameters on the left-hand side, potentially because of its increased lipophilicity. Through the addition either of just a single heteroatom, you can see that some of these properties start to level out and potentially even become more favourable. Now, how does a chemist overcome these issues? Because we know that many drug molecules already contain some aromatic rings in the system. Well, what we are able to do is that the chemists will often fuse aromatic rings together to try and aid with this lipophilicity penalty. By doing so, it's said that if you create these fused rings, you enable for better solubility and you move towards potentially more favourable log D. It has been a short talk, but a very important talk. In this talk, it should have been critical once again about lipophilicity. Lipophilicity is a major contributor to compounds failing preclinical development, and you must pay attention to this property as you start to move through the drug discovery pipeline. If not, it can lead you to potentially some off-targeting effects and perhaps preclinical toxicity. We know that Lipinski's rules wasn't enough to be able to understand what is happening to our molecule as we start to push it through the drug discovery pipeline. The most common of metrics used are the ligand efficiency, the lipophilic ligand efficiency, and as most recently, the property forecast index. It is advised that you use not just one metric at a time, but you use a combination of metrics to be able to understand exactly what is going on about your molecule. You saw here the comparison of ligand efficiency as well as the lipophilic ligand efficiency. You saw as that you occupy the right-hand side of the diagram, that you start to move into more ideal drug space, but you also must keep an eye out of what sort of interactions are you making. Are you just adding lipophilicity to your molecule for the sake of it in order to boost your potency? By using that Hopkins paper, you are able to understand through the addition of some functional groups how much of a potency gain do you in theory need to see to ensure that that change was significant or meaningful. It's advised that you use metrics to guide your compound design because it should limit your undesirable physiochemical properties later on. Lipinski is a good rule to use, however it's used to use other forms of analysis as you move through the pipeline. Remember, each of these has its disadvantages, but it also has massive advantages, so use them wisely. This talk to you was brought to you by the Wellcome Centre of Anti-Infectious Research, the University of Dundee, Scotland, UK.